physical knowledge to generate a set of physically meaningful unit-free variables in advance. Any formula discovered later still makes physical sense. How much automation is appropriate? Many symbolic regression tools today emphasize automated equation discovery, but when it comes to uncovering real physical mechanisms, such full automation can be irresponsible. The model itself doesn't know which structures are physically meaningful and which just coincidences. It simply searches for the best fit. But the best fit is not always the most interpretable. Scientific formula discovery is a fitting competition. Is not a fitting competition. It's a process of physical insight. What truly matters is interpretability, not just accuracy. So the entire process requires manual intervention and guidance, making it a human-computer interaction process. So we note introducing a new symbolic regression algorithm we have developed is a full transferable strategy for discovering scientific equations. It's designed to balance accuracy, simplicity, physical meaning, and teamwork between human and machine. We call it machine phenomenology. Now I'll show you how this method is applied to real scientific problem classified in fossil birds. Fossil birds remain one of the great mysteries of astrophysics. We have not detected many of them, but only few have been seen to repeat. The majority appear to be one-off events. That raises a big question. Are all fossil birds actually repeaters? If we can classify them, we might get clues about their physical origins. There's a need for a method that is both accurate and interpretable. We propose that there's a hidden physical property which can derive from the observable parameters that help distinguish them. We use the first fast-readable catalog released by the CHIME, covering a frequency range of 400 to 800 MHz. This catalog contains 136 radio bursts, 474 non-repeaters, and 62 repeaters. Each subburst was treated as an individual sample, giving us a total of 594 subbursts. We used the CHIME Catalog 1 as our training and test set. Due to the class imbalance, we applied the smooth technique for sample balancing. CHIME Catalog 2 from 2023, which includes only repeaters, were used as an additional test set to check generalization. The bandwidth is limited to 400 MHz, but due to the small sample size, we kept this data for modeling. The first step is key feature selection. We trained 100 neural network models, each using all 48 observable parameters. The neural network used can be of any form, but we employed a simple multilinear perceptron. We input 48 features to predict the probability of each category by analyzing feature importance. With SHAP values, we counted how often each feature appeared in the top 10 rankings across all training runs. This is a display of the feature importance rankings after training a specific network. We found that 6 parameters consistency ranked highly across almost all models. Boxcar weights were not selected because it represents the total duration of an entire burst. This covers four essential aspects: spectral shape, radiation intensity, timescale, and distance information. These six parameters selected by the neural network provide a relatively comprehensive description of fault burst observations, with each parameter contributing a unique aspect that can't be replaced by any other. All six parameters are essential; none of them can be left out. Further tests showed that, even when using only these six features, neural networks still achieved high classification accuracy. This suggests that the difference is not dominated by any single indicator but rather reflected in multiple observable aspects. This is the first hint we see in this study that two types might originate differently. In this process, perturbation analysis acts as a probing system to help evaluate the relationship between variables. We used a trained neural network, which was trained on the six key features selected earlier, and recorded the model's predicted value for the current input sample. We perturb each input variable's x by one standard deviation and calculate the model output. By jointly perturbing pairs of variables, we calculate the nonlinear interaction eta values to assess whether there is coupling between them. This method is rough and not rigorous, but it's relatively intuitive and provides useful hints. We don't try to write formulas based on eta, but instead use its information to support the construction of dimensionless variables in the next step. For example, if subburst width and peak frequency show strong coupling in the perturbation analysis, we would prioritize combining them into a dimensionless term. Next, we use the Buckingham pi theorem, which says that an equation with n variables can be expressed as p-dimensionless parameters, where p equals n minus k and k is the number of dimensions. Based on this, we think about how to combine the variables to neutralize the dimensions and form a true pi group. If it works, we keep that combination. If not, we make adjustments. Science still involves three fundamental physical dimensions: mass, length, and time. We can construct three-dimensionless combinations plus already dimensionless spectral index R, yielding four variables in total. In other words, perturbation analysis tells us which variables might be combined, while dimensional analysis tells us how to combine them. Here's where it gets interesting. Unlike normal regression, symbolic regression does not assume any form of the formula in advance. The core idea is to treat a mathematical formula as a binary tree, where each internal node is a mathematical operator, and each leaf is a variable or constant. I will briefly introduce the process. It randomly generates a bunch of initial formula trees, score them based on how well they fit the data, keep the good or oldest ones, and apply genetic operations like crossover mutation to create new ones. The mutation operator is akin to random mutations in DNA, such as randomly altering a node. For example, changing a plus sign into a minus sign. The crossover operation involves swapping paths between two parent formulas. These genetic operations don't always guarantee improvement in the formula. However, through the selection mechanism that considers both fitness and complexity, we retain the formulas that perform best. The evolutionary process continues, gradually improving the formulas. Finally, the best performing and simplicity formula is selected as the final model. We utilize the PYSR framework, a tool based on genetic algorithms, and capture most of the parameters at their default setting as much as possible. We set the model selection criterion to best, which considers the formula's complexity compared to the score criterion. We restrict the variable operators to addition, subtraction, multiplication, division, and power to keep the formula simple. Addition and subtraction were given a complexity of 1, while other operators were assigned a complexity of 2. Because this is a classification problem, we use the classical sigmoid function to convert formula output in a probability. The training minimizes the cross-entropy loss function in our optimization. We prioritize the simple formula that still achieve acceptable accuracy. This is because the data contains observational errors and labeling uncertainties. We don't expect a perfect separation between them at this stage. Because the symbolic regression is a stochastic process, we run it 10,000 times, generating 10,000 candidates, and rank them by score and recall. Most of formulas are in relatively complex form. The result is the variable pi3 rarely appears. Combination pi1 and pi2 appear frequently, indicating that time frequency features are most important. One of our best some simple formulas looks like this. Of course, formulas including pi3 remain among our candidate solutions, awaiting more data to refinement. Although DM ranked high in feature selection, it didn't appear in the symbolic regression formula, reflecting the different expression capability of neural networks and symbolic regression. Neural networks capture complex nonlinear mappings, while symbolic regression seeks simple, explicit relationships. Even while maintaining formula simplicity, the model performs well on the first catalog. The left chart shows the confusion matrix for classification, where 415 non-repeaters were correctly classified, and 86 repeaters were correctly classified. The right chart illustrates how the accuracy changes as the classification threshold is adjusted. We can flexibly adjust the threshold, and in this case, the threshold is set such that if the formula output is greater than 0, it is classified as repeaters, and if it's less than 0, it is classified as non-repeaters. To check robustness, we directly apply the NDR formula to the new catalog from 2023, which contains only repeating fast-reading bursts, as shown in the figure. The model remains stable, showing good generalization across datasets. These six overlapping repeaters were originally labeled as non-repeaters in the first catalog. We kept them in the NDR fitting as a probe to test the method, and we can see only one was misclassified, which gives the best result compared to existing methods. Now here comes one of the most intriguing findings. The classification scores output by the NDR equation show a bimodal Gaussian distribution. The stacked histogram displays repeaters from catalog 1 in black and non-repeaters in gray, with the hatched regions indicating sources is limited by the 400 MHz bandwidth. The orange histogram represents catalog 2 repeaters. The solid color curves show the bimodal fit, brown for repeaters and green for non-repeaters. The solid black line shows their sum. Firstly, lower mean Gaussian contains most non-repeaters. The second peak mostly contains repeaters. Some non-repeaters fall into the high mean region, possibly indicating they are repeaters that haven't been observed repeating. This bimodal pattern resembles the two population structures seen in gamma-ray burst, based on their T-net. It suggests that fast-ray bursts also contain two physically distinct populations. Our method intersects the candidates with those from other methods, indicating what we call the strongest candidates. This work is still under refinement, but so far we have obtained some meaningful physical indications. Of course, this part is only an interpretation based on the final formula we obtained, given its good accuracy and the generalization ability. Repeaters tend to have narrower, steeper spectra and long durations compared to non-repeaters. Additional results. The classification of fast-rate bursts based on spectral shape-related parameter is of the highest importance. Our formula doesn't include DM or flux, indicating that within the current redshift range less than 1, repeaters and non-repeaters show no significant difference in cosmological distance and luminosity. Because of these combinations, redshift effects are naturally consoled in our formula. Therefore, our formula reflects intrinsic physical properties independent of observational distance. There are still many limits. Our current data is limited to redshift less than 1. Second, the number of DM measurements for repeaters is still limited. While restricted our ability to fully evaluate the role of DM due to the instruments of frequency band limitation. The bandwidth value are truncated to 400 MHz, so the values in catalog are not entirely precise. Although the classification formula performs well on the current data, more data is still needed to optimize this initial classification formula. One reasonable perspective is that so-called non-repeaters we see might just appear that way because of observational limitations, like being too far away or have really long repeat cycles. So we simply haven't caught their repeats. From this angle, they could actually be the same kind of object, just with different activity level. Our work might just be identifying the more active repeaters. This also highlights the need for larger samples and long-term data to keep testing the link between repeater behavior and physical nature. Our method, along with others, has confirmed the presence of classification. However, the underlying mechanism that lead to this classification remain unclear. Professors also reminded me to be cautious when explaining the origin of facial birds. It is possible that these two populations originate from different progenitors, or they might share the same progenitor but differ in their radiation mechanisms. Another possibility is that they are the same type of star but with different properties. To make a more detailed distinction, our current work hasn't reached that level of refinement, but our method might be improved to achieve this. We may incorporate more physical models to refine the process and make better judgments about the model. This will be part of our next step. We believe this work has contributed to advancing our understanding of fossil reversal origins. In summary, we are working in an unknown domain facing challenges such as data imbalance, insufficient samples, potential label errors, and a large number of primes. Moreover, this is not a regression problem, but rather a classification problem, where we derived a formula. Despite these challenges, we have made meaningful discoveries. This already serves as a strong validation for our methodology. Thanks very much.
Well, I'll ask, first of all, congratulations both to you and to Wang Yu. And I would like to ask Wang Yu to make some additional comments.
Okay.
A perspective.
Okay. I participated in this work. I collaborated with Liu Yang. So this repeater, non-repeater, as Professor Dili said in the morning, it's still a mystery. And we don't know it's from the same progenitor or different progenitors, but there are many models. So this work is, I think we are pushing the machine learning and the human being collaboration to the limit. So you can see first from the catalog, we take the trend data, hundreds of 300 of bursts. So it contains more than 100 parameters. So the first step is to select the most important one, significant ones. This is by machine. We trained 100 networks, a simple network, to do the classification. And for each network, we take the top 10 parameters, because by some machine learning technology, you can find those most important parameters. Then we accumulate the number of these top 10 parameters to have the final distribution of the most important parameters. So we select 6 And interestingly, this 6 covers the whole description of the spectra, including the mu p, which is the peak energy of the spectra, and delta mu, that's the range, and delta t, the time and some spectral index, and also dispersion measures and flux. Then we are thinking, so we have 6 parameters at hand. Then we are going to construct a function using these 6 parameters to see if we, by using this function, to separate the non-repeater and repeaters. But 6 parameters are a lot. People never have been done using machine to search for 6 parameters function. Normally, like 2, 3, because they can rediscover the Newton's law, Kepler law, only 2, 3. So we are 6. So we thought a lot, then found we can use the dimensionless analysis using the pi theory. Here we have units. And the pi theory tells we have the time, centimeter, and the gram. So we can reduce 3 parameters using dimensional. So we have 6 reduced to 3. But how to select the 3 new parameters by the combination of 6 parameters? We did a lot, again, by human. The way is to perturb the parameter. Like we have selected 6, then we can change 1 parameter, or we change 2 parameters. Then to check how the result changes. So the result will increase, decrease, linearly or non-linearly. So in this way, more or less, we know the relation between each 2 parameters from these 6. So by this knowledge of human, we constructed those pi group. We say pi groups. So we have 3 pi groups. Yeah. So we have reduced the parameter numbers. Now the next step is to find the formula. Find the formula, we are applying a standard way of machine learning, which is called the genetic algorithm. And I spent many days on it because the machine taught me really thousands. I think I have checked more than 10,000 of equations I have checked. Because the purpose is not to select the most accurate one, but a simple and accurate. So as you can see, finally, we have an equation very simple. Liu Yang, can you show the equation? Because that equation, this one. This equation. You can see we only have the mu p, the peak frequency, delta mu, the bandwidth of the spectra, and the delta t, the duration, and alpha, the spectral index. And very simple, you see. And so when you put, actually we have more parameters, but they diminished during the symbolic regression. We have also the dispersion measures, but it doesn't appear in the final formula, also the flux. This is very interesting. But as you can see, delta t, if we have redshift inside, because this equation is redshift independent. So delta t is, if we consider the cosmology expanding, your delta unit should multiply by 1 over z. And the left side, you have divided by 1 over z. And they cancel each other in this equation. So this is very interesting. Only by this regression, you know something works, but something works internally, not affecting the final results. And also for the flux, it can be useful, but it brings very little change of the final results, so we didn't put it inside. So when we have the equation, we have the observational those quantities, like mu p, delta mu. Then this equation computes all these parameters and gives output to be plotted on this histogram. So x-axis is all the input from these equations. Then you can see it forms these 2 Gaussian distributions. And the left one, those gray one, so we need to compare with the the catalog. You see the left one, most of them are the non-repeaters, and on the right side, it's the repeaters. So we have two catalogs because the Chime published two catalogs. The first catalog are the black points plus these gray ones. So you see, so this part, all the black points are within the second Gaussian, and most of the gray ones are within this left side Gaussian. And when we apply this equation again on the second catalog, we will never use the second catalog to train this network. So the second catalog only contains the repeaters. So these yellow ones, you see, they naturally are located on this second one, on the second Gaussian function. So this tells us this non-repeater and repeater, they have some differences, but we don't know it's intrinsic or radiation mechanism or something else. And this is the result.
Right. I think this is.
Oh, it doesn't work. No battery.
Fantastic work and very sort of working. But from this morning's from my talk, I suggest there's an alternative explanation of the distinction between repeating and non-repeating fast radio bursts. In practice, they may turn out to be similar in that. So the last slide presented here, the last atom is about the progenitors, the origin, but they could also be, they correspond to two different stages, like the old repeating FRB are much younger, and all the rest is the sort of main sequence lifetime of the FRB. So to test that hypothesis, maybe we can give you all the large burst set. Like for example, we have 15,000 bursts from 2024 0114A. We now have like 8,000 for 121102 and a few hundreds for 190520, a few thousand, 2,000 for 2021, 1114. So there are a few of the sources, and run similar experiment to try to find the distinguishing formula to describe the bursts from the same set, but somehow separate them into two categories. I haven't have a clear idea. The obvious candidate is, say, for example, all this source has a bimodal energy distribution. So we can have a separating line, separating the log normal low energy part and the sort of power law high energy part. But by doing so, you have to remove the energy from your equation because you're already using the energy as the prior, and see whether you can also find the distinction between the pulses from the same source, but they reflect two different population or two different emission mechanism, or we devise some other separation. For example, the extremely active episode and the rest. That may also have distinctive traits. So that would bringing additional knowledge and value to a work, right? So that either shows the distinction between single births and repeating sources, real extinctions, or it's a reflection of some observable traits. And yeah,
Only from your data you have many bursts from one single source.
Right.
Yeah.
I think that would be quite curious.
Yeah. Yeah. So I think so. This method is very general, but it's regression method.
I have another curiosity. You may not have to go out to do it. I'm just curious. For example, if you apply the same mechanism to, say, the stellar spectrum, and then can you distinguish between, say, massive star and low mass star?
I think in order to test your procedure, you can do it with a very known physical side of a more known problem. Right? And you take it.
Yeah. Use the microphone so
Just
they...
the data was available 100 years ago.
Oh, I don't need it. I have both at once. Oh, yeah? This is for the GoToMeeting, the microphone for the GoToMeeting. Oh, yeah. Oh. You. Oh, you need 2000.
No, we are waiting after. Excuse me. We will speak after coffee.
Oh, yeah.
Okay, but you will show me before coffee. Now, during coffee, you show me the thing. Because what were you saying?
No, it's just a comment that because I didn't know this method, that it would be nice to be tested with known physics problems older, where we do know the right formula. And but you were saying that
Can be discovered.
yes. Now I imagine that this was checked in older problems, but in problems like this where you are very new field, it's complicated because it's so many uncertainties that I don't know. It's a long shot, but okay.
They just started. This area just started.
Yeah.
Using machine to find the formula. But it shows it's very powerful.
But if there are these examples, just show us where they made the rediscovered to us.
They did it for the Feynman's book. They can discover the formula in Feynman's lectures.
We have coffee break now. And can you the speaker of the text? Does not work, this thing, or does it? Eh?
It doesn't work here, but it works for people outside.
Ah. Per favore, li metta a posto per domattina. Set of lectures, but I would like to punctuate as much as possible the step that we are through, and in the next, let's not lose time. There have been different time in astrophysics in which certain sectors have born and been developed independently from each other. The discovery of the pulsar, the discovery of the remnant of the supernova, and the supernova remnant, the pulsar, and the supernova remnant with different components, and also the gravitational collapse. And all these topics have been developed separately from each other. But even the appearance of the jets and so forth. Then suddenly, we have been working for 50 years on building a model for GRBs. And in these 50 years, it has been very, very, very laborious, because we had to understand the physics of the. Well, one thing was to have introduced the black hole with the equation of Kerr. One thing has been last year, as you have seen this morning, a beautiful example to understand how, in astrophysical condition, a black hole can work. And finally, to find a way to measure the mass of the black hole at least from the neutron star. But at the same time, what we have started to analyze has been, can I project the two papers? Yeah. The two papers. Yeah. We have any one of the two. Yeah. Any one of the two. For example, this one. This has been by far the most complex paper we have managed to write on a GRB. Not the most complex, is the simplest, but at the same time has been the one in which we have localized 7 different episodes of GRB. And let's see some images quickly. This is practically the summary of what we have understood, and up to now. And the most interesting thing to me has been to understand in GRBs each different fundamental episode. For example, we have understood that at the trigger of this GRB, at the trigger of this GRB, there is a very, very, very intense emission lasting of the order of few seconds, and energy very big, 10 to the 53 in this case. You see, can we look at the time here? Because yes, without time it's very difficult. Which lasts a few seconds. and very, very energetic. And then while we go on, there are other processes appearing, also very energetic, the number 2, the number 3, the number 4, and the number 5, the number 6 of the afterglow, and the 7th, when it appears, is the number 7, when it appears, is the remnant of nickel decay, which was generated from a supernova in the early phases. Well, this has been quite clear, these 7 episodes plus the decay of the nickel. But now we are using, thanks to the work of all the collaborators, we are using this result in order to go back to the physics of the GRB. Because now we have seen all these effects. But to me, the most spectacular are if you look back in time of this very, very complex initial phase after 10 to the 5, 10 to the 6 second, you start to have an asymptotic behavior. What happens? You start to have an asymptotic behavior. What happens? We are lost.
No. I have this, but oh yeah.
We start to have an asymptotic behavior in time. And in other words, there is a very big difference between the first 10 to the 6 second. Here, when it is here, is the last phenomena of this early GRB, the last one being the decay of the tritium. And then you start to have the asymptotic behavior. And the asymptotic behavior is carried on by 3 afterglow. People don't realize this point. They always speak about an afterglow. But there are actually 3 afterglow. One afterglow in the optical, which leads to the pulsar. One afterglow in the JEV, which maybe we will show you more explicitly, and one afterglow in the X-ray. And we have done a very, very interesting diagram with Guangqui, and we will show in the next day, showing that these 3 peaks correspond precisely to the spectrum of the remnant, for example, in an object like the crab. Now, the fantastic thing which is coming out, which to me was really totally unexpected, well, nothing was unexpected, well, this was one of the things unexpected, is that if you take any GRB and you extrapolate up to 1,000 years, whatever GRB, you have the power law you extrapolate to 1,000 years, in all the GRB which we have managed to look at,